Okay, so the last talk of this last session is by Clément Chavanon. So he has worked on formalizing firewall policies, and he's going to tell us about this.
Thank you, Roger, for the introduction. So here I'm going to talk about verified compilation for packet filtering. So we built a PfComp, which uses binary decision diagrams as an intermediate representation. So this work is a joint effort between Frédéric, Besson, Tristan, Ninet, and myself. So in networks, firewalls are essential security components because they allow to filter the malicious traffic and reduce the possible attack surface. Configuring such tools is often a complex task. It requires to write a list of rules in a certain domain-specific language. And for the people who work on the compilers or interpreters for this language, they face two main challenges. The first challenge is the challenge of efficiency, because we don't want that our compiler introduces some higher latency or lower throughput or even traffic loss. And the second main challenge is the challenge of correctness, because as firewalls are security components, we don't want like the compilers or interpreters introduce some bugs because it could lead to security issues or legitimate services unavailability. So that's why you work on PfComp, which is a verified compiler, which uses from a filtering policy, it produces efficiency code by using binary decision diagrams, or BDDs, as an intermediate representation. So in this presentation, I'm first going to present background of the project, so what are BDDs and the related work. Then I will focus on the compiler internals, as well as the benchmark we run on the compiler. And finally, I will conclude. So binary decision diagrams are directed acyclic graphs, which encode Boolean functions. So for example, here we have a binary decision tree, which is a BDD, which encodes the Boolean function x1 and x2 or x3. So each node of the graph contains a Boolean variable and has two children. So the left child, which encodes the fact that the Boolean variable evaluates to 0, or the right child when the Boolean variable evaluates to true or 1. So evaluating a Boolean function is equivalent to traversing the BDD from the root to a leaf, and leaves being either true or false values. In our compiler, we manipulate a specific form of BDDs, which are reduced and ordered BDDs. So ordered BDDs mean that you fix a total order on the Boolean variables which compose the BDD. And choosing this order is very important because different orders can heavily influence the size of the BDD, so the number of the nodes in the BDD. And reduced BDDs mean that we will merge all the identical subgraphs. So for example, in this binary decision tree, these subgraphs are identical. So the reduction phase will merge it so that the left child of the node containing x1 and the left child of the node containing x2 will point to the same node in the memory. So trying to formalize compilers for packet filtering and uses decision diagrams is not a new idea. So for example, we can cite the work on JIT-K, which is a formally verified JIT compiler for a backleft packet filter bytecode. We can also mention the work on the software-defined network side with Netcats, and especially the work of Smoka and other authors on a compiler that use forward decision diagrams as an intermediate representation. So FDDs are a generalization of BDDs in which each node contains a test on the packet field, and leaves are either a drop of the packet or a forward of this packet to another port on the switch. And finally, we can also mention the work of Christensen and Fleury, which worked on a compiler which uses interval decision diagrams, which are not binary data structure, but n-array data structure. So each node of these IDDs has a packet field, and then each branch contains an interval to which this packet field evaluates to. The main issues with those works were either a too much restricted domain-specific language or a lack of mechanized correctness proof. So that's why we work on a PfComp. So this is an example of a filtering policy that we write in our domain-specific language. So first, the programmer described the data structure that encodes the packet. So here, a packet has only two fields, the source IP address and the destination port, which are unsigned 32-bit integers. And then the programmer writes the policy, which is a list of rules. Its rules contain a condition and an action. So a condition is a logical formula over predicates. So a predicate is a test on a packet field. So for example, dport is greater than 10 is a predicate. And then an action is either reject or accept, to reject or accept packets. So this syntax is really inspired by the netfilter tool in the Linux kernel. But here we have a more simpler language because we only deals with reject or accept actions. For example, we have no logging or stuff like that. We use packet filtering as a use case, but as long as you can encode whatever you want to filter with our domain-specific language, you can filter more than packets. And the semantics of this filtering policy is simple. The rules are match in order against the packet. And the first rule that matches these packets defines the action to perform on these packets. And if no rules match the packets, then the packet is rejected by default. So this is an overview of the compiler. First, the front-end compiles a filtering policy into binary decision diagrams, on which we made some optimization that I will explain later. And then the backend compiler compiles a binary decision diagram into C code. And the entire compiler is programmed within the copproof instance, which enables us to prove the correctness of the compiler. So by the correctness of PfComp, I mean that if you have a filtering policy P and a C program C, then if PfComp compiles P into C, we want that the results of the execution of the filtering policy with its semantics and the result of the execution of the C program with its semantics are the same. And in the theorem, I write C-lite because we use the C-lite semantic of the C programming language, C-lite being an intermediate program language of the concert C-verified compiler that David just mentioned in the previous presentation. And then, once we have the C code generated by PfComp, we can use a certified C compiler, such as Concert, to produce assembly code, and then have an end-to-end correctness proof from filtering policy to assembly code. So the front-end part is divided in multiple steps. First, we flatten the policy, so the policy is transformed in a unique and logical formula over predicates. So, for example, the policy above is transformed into the logical formula below. So this transformation is proved to be correct. So if the filtering policy rejects the packet, then the logical formula evaluates to false. And if the policy accepts the packet, then the logical formula evaluates to true. But we do one more thing before this transformation, because in this filtering policy, we have the intuition that the first rule seems to be redundant, because if we remove it, it does not change the semantics of the policy. In fact, the set of accepted packets will be exactly the same, so packets which exactly match the second and the third rules, and the rejected packet with all of the others. So removing these rules does not affect the semantics of the policy. So we have a pre-processing phase in the compiler that removes all these redundant reject rules, which reduces the size of the policy and the associated logical formula over predicates. So what type of data structure we want to obtain is shown on the slide. So this is the decision diagrams on which each nodes contain a test on the packet field, and leaves are either accept or reject. However, we do not directly implement those data structures. We work on an abstraction of predicates into Boolean variables, which enables us, for example, to reuse state-of-the-art algorithms on variable reordering for BDDs. So the BDD will contain Boolean variables in the nodes, and then the compiler will also return an environment that maps each Boolean variable to the associated predicate. And the reject leaves become the false Boolean value, and the accepts becomes the true Boolean value. So to obtain these BDDs and these environments, we have multiple steps in the compiler. So first, we extract the list of all of the predicates contained in the logical formula. From this list of predicates, we build the environments that map each predicate to a Boolean variable. And then we take the initial logical formula of our predicates and the environments, and we generate the associated Boolean formula. Once we have this formula, we can build the associated binary decision diagrams. So here we use an already existing Coq BDD library developed by Brébant, Jourdan, and Monio. And aside from building the associated BDD, which correspond to the initial filtering policy, we also return the environments of Boolean variables to predicates. However, working with an abstraction of predicates into variables has a major drawback, is that it does not encode the predicate logic. So for example, that some predicates are incompatible with each other. So for example, in this BDD, if we take this path, so this path is exactly encoded by the Boolean formula on the right, by the logical formula on the right, sorry. But there is a contradiction in this formula because the source IP address cannot be equal at the same time at to 10.0.0.1 and to 10.0.0.2. So this path in the BDD is infeasible. So we need to do some optimization to remove this infeasible or redundant path in the BDD. So what kind of optimization we integrated in PfComp is variable reordering. So we delegate this task to an external unverified library, which is queued. And we also do BDD restriction to remove these redundant and infeasible paths in the BDD. So BDD restriction was first published by Kuder and Madre. And we have this property that if we have an environment of evaluation function eval, Boolean value b, and two BDDs phi and beta, we want that the restriction of phi and beta follows the following property. So if phi evaluates to b in env, and if beta is a tautology in env, then the restriction of phi over beta should also be b. So what kind of tautology we built with our logical formulas? This is what type of formulas we want to build. So this formula is a tautology in the predicate logic, and it simply encodes that the source IP address cannot be equal at the same time at two different values, and this is the same for the destination port. So then we want to restrict our BDD example over this tautology. So that will result in this edge being remapped to this edge. So that if we have a packet, incoming packet that have source IP address being equal to 10.0.0.1, but a destination port being not equal to 22, then it can be directly rejected by the filtering policy. So the infeasible path we had earlier, it just removed with this restriction operation. So to summarize, this is an overview of the front-end compiler. So first we have a filtering policy. From this filtering policy, we fix default predicate ordering. Then from this ordering, we build an environment of variables to predicates and the Boolean formula. We have this unverified library that will return a new environment, a new order list of Boolean variables, which is expected to be better than the initial ordering we fixed in the previous steps. And once we have the new order of variables, we can build the new environment of variable to predicates, which is just a permutation compared to the initial environments. We build a new formula and the associated BDD by applying the restriction to remove the redundant and infeasible paths. Okay, so for the backend compiler, I just drawn the BDD we obtained at the previous steps. And I also add some labels to the node. So this is the case in implementation. Each node is associated with a unique name. The first thing that the backend compiler will do is just compiles the data structure that encodes the packets. And then it generates the filtering function, which takes a pointer on a packet as a parameter, and then lists a sequence of if-then-else statements. So each if-then-else statement corresponds exactly to one node in the BDD. And for example, the node label 1 in the BDD corresponds to the if then else statement labeled $1 in the C code. So the condition inside the if corresponds to the predicates, which is mapped to the Boolean variable in the environment. And then either we jump to another node in the BDD by using a goto statement, or either we return 1 to accept packets, or we return 0 to reject packets. So I'm going to present the backend correctness theorem that we prove inside the Coq Proof Assistant. This will look like a basic correctness theorem, but we have an hypothesis that we need to do to prove this theorem. So this important hypothesis is the following one. It says that the packets inside the memory, C memory, concert memory, is well-formed, meaning that the pointer PTR that we pass to the filtering function effectively points to a valid memory location, and that it effectively points to a packet, that there is a packet in this memory location. So the second hypothesis that compilers compile a BDD into some C program with the filtering function filter, and that the BDD evaluates to the Boolean value B. And from that, we want to show that we can start from a call state, calling the function filter with the argument PTR, and by executing the semantics of the C-Lite program, we can reach in one or multiple steps the return state that return exactly the same Boolean value that the BDD was evaluating to. So here it's B. So the way that we prove this theorem is by using a standard formal simulation that was presented by David just earlier. I will just remind what is this formal simulation with a more graphical view. So imagine that we have two states in the BDD semantics and in the C-Lite semantics. So BDD is the source language and the C-Lite is the target language. And that we build some binary relation that links the two states. We also assume that from the state sigma BDD, we can reach in one step sigma prime BDD, which is a number of states of the BDD semantics. And we do that in our semantics. We do not produce any trace. So I put here epsilon to say that traversing the BDD does not produce any trace during the simulation. Once we have the hypothesis, we want to show that first we can reach sigma prime C-Lite from sigma C-Lite in one or more steps, which is a pre-simulation. The trace should also be the same, so here epsilon. And finally, we want to show that these two states that we obtain, so sigma prime BDD and sigma prime C-Lite, are related by the same binary relation than the two previous states. So with an example, so in our BDD, we begin at the node labeled 1. We're assuming that the variable x1 evaluates to true in the environment, and we jump to the other node labeled 2. So, of course, in the proof, we prove the theorem for all of the possible evaluation environments. In the C-Lite code, we're starting by calling the function filter. Then we want to execute the first statement, which is a goto to the compiled root of the BDD. And our binary relation says that each node labeled 1 in the BDD is linked to $2 statement in the C code. Sorry, each node labeled n in the BDD is linked to the goto$n statement. So this is the case with labeled 1 in this example. So we continue by simulating the C program. We will execute the if then else statement. We also assume that in the environment x1 evaluates to true. So here, this is a Boolean variable, but of course, in the real theorem, we manipulate predicates. And we obtain, we jumped to the then branch, which contains the goto$2 statements. And the binary iteration is valid for any node labeled n, so it is valid for these two states, with the label being 2. Okay, so about the benchmark we run the compiler. We wanted to test two main things, which were the scalability of PfComp in terms of compile time, a number of nodes generated in the BDDs, and also the memory consumption. And we also wanted to check that filtering efficiency was good. by comparing different modes of PfComp without or with the different optimizations. And also, we compared the PfComp to the Linux kernel tool and the tables. So if you want more details about the benchmarks, especially the comparison to the Linux kernel, I encourage you to read the paper. In this presentation, I'm going to focus on the filtering efficiency for the different modes of PfComps. So the different modes we've compared in those benchmarks were first naive compiler. So we have a mode of PfComp that directly checks the filtering policy and compiles it into C code that naively evaluates the rules in order without using the intermediate representation, being BDDs. The level 0 using BDDs, but we don't add the BDD restriction in this optimization level. And the most optimized version of PfComp is using BDDs and variable reordering plus BDD restriction. So it's really difficult to run benchmarks on real realistic data. So we use a firewall log found on the internet. And from this firewall log, we create packets and as well as filtering policies. And of course, to be able to run the compiler, we extract the code into OCaml and use the OCaml native compiler. So those are the results of these benchmarks. So in green, you have the naive compiler. In blue, the compiler with optimization level 0. And in orange, the compiler with optimization level 1. So the first thing that we notice is that the most optimized version of the compiler outperforms in terms of filtering efficiency the other compilers. So this is because in the filtering policy there are some redundancies between the predicates. So the BDD restriction is able to remove a lot of nodes in the BDD, leading to lower filtering times or higher throughput. And there is one more thing we can see. There are some missing points in the blue curves. This is because as the BDDs contain too many nodes, the compiler was not able to produce in a reasonable time C code. So we can't have checked the throughput of those missing files. So this benchmark showed that BDD restriction is helpful for the filtering efficiency, but also for the scalability of the compiler. So, to conclude, with this work, we created a verified compiler for packet filtering, which compiles filtering policy into C code and uses binary decision diagrams as an intermediate representation. We make some add-ons to the Coq library of Brabant, Jourdain, and Monio, particularly a proven correct restrict primitive, but we also had a garbage collector, for example. And we also made a scalability and filtering performance benchmarks to show that even proven correct compilers can produce efficient code. But there is a lot of work to do. For example, we would like to extend the language and being able to support not only reject and accept actions, but more terminal nodes. For example, a drop, which has a different semantics from reject, but also, for example, a logging system, as well as a stateful firewall. We could also look for another performance metric, because in our compiler, we wanted to reduce to the minimum the size of the BDD. However, if we have a priori knowledge on the packets we receive, we could be able to create a decision diagrams that minimize the path depth and not necessarily the BDD size. And finally, we would want to formalize not binary data structures, but NRE data structures that are more specifically interval decision diagrams, like in the work of Skutsinson and Furry. Thanks for listening. I will be happy to take some questions.
Thanks, Clément.
In the paper about BDDs that you cite, there were several ways of doing the BDDs, especially the hash consing. Yes. There's one way in which the hash table is implemented, design some maps from integers to. Is this the one that you're using?
Yes. So David is referencing to different modes of implementing the BDDs in his article, and we use the deep embedding, which maps each an integer through a node, and we have hash counting and memoization to have a more efficient implementation. But it was because it seems to be the simpler version to use at the beginning. But we may have looked for the shallow embedding also to have less memory consumption.
I have a question about the deep embedding. Would you think it appropriate to use the functional arrays that exist nowadays in OCaml in order to do that? Because that would be much more efficient than the map.
That was an idea that was evoked by Frédéric, but I can answer because I am not the expertise here.
Other question? So you made me very curious about the comparison to the Linux thing. So
Yes.
maybe that's on purpose to make us go read the paper.
Yes.
But can you still say a few words about like what the comparison looks like?
If you want I think I have the graphs.
Even better.
Yes. So the setup was we have on the same host machine, we have a client that sends packets to a server, and we use some tools to measure the throughput. So in NF tables, you have two different implementations. So NFT, which is a naive lookup of the rules in order, and then NFT sets, which is an optimized version of NF tables, which use like hash tables and has a constant time lookup for each packet. And so PfComp is represented in PFC, and the number just next to the name of the compiler is the number of predicates when in one rule. So if 2 means that we have a conjunction of 2 predicates in the same rule. So the benchmark showed that we can't compete with the very optimized version NFT set, which has a constant time lookup. However, the PFC performance was not that bad compared to NFT set, and outperforms the naive version of NFT. The time complexity in the benchmark run or the inverse or the square roots, because the filtering time complexity is the square root, so the throughput is the inverse. So that was the results we obtained.
I see you're pretty close. Can you just say everything is compiled using CompCert, including the Linux code or the Linux code?
Yeah, for those benchmarks, we also we use CompCert to compile to binary code. So yeah.
But maybe a compiler with more aggressive optimizations will make the difference smaller or bigger between the.
It could make the difference if you had a more aggressive optimization. Yeah, if you use GCC, for example.
I had one more question, but yeah, maybe we can go.
Hi, my name is Cesar from MPI. I have a question. Is NFT set also preprocessing the rules? You said, do you have this step where you preprocess the rules and you minimize the set of the rules?
I don't know how NFT set works exactly, but I think that it works differently because it seems to be more an interpreter than a compiler, and it constructs hash tables when looking at the filtering policy. So I don't have the exact function of NFT set. Sorry.
One more question: as the if statements that you put in the sequence in a certain order to test the closes, maybe you can learn through the data that you get in practice that with one particular if you can fail earlier than another. So do you have plan, or do the other implementation use techniques based on changing at runtime the order in which the if statements are tested?
So your question is about to change the order of the if in function of the packets we receive?
In function of the practical queries you get, yes.
I think that the response is, I think that it was what I mentioned in conclusion. because there are some algorithms to minimize the death path if you have an a priori knowledge on the packet you receive. So these algorithms are able to produce decision diagrams where you reach a faster leaf if you know what packets you are receiving.
Yeah, my question was whether you can change the code online to reflect on the data that you get. But
no, in the actual compiler, it cannot be done.
okay. Yeah. Thank you. Okay, so I think we're reaching the end of the session. Thanks, Clément. Maybe Brigitte, you want to say closing words?
Yes, I just wanted to thank all the authors for submitting to CPP, and hopefully we'll see some of the submissions also next year. It would be great to see them again, whatever new things you have come up with. And I really enjoyed many of the talks. I really appreciate the questions and the engagement of all the authors and participants here. So hopefully we'll see each other again next year at CPP. And you help us make it a continued success. Thank you.